So we're ready to begin, and let's go ahead and jump right into it. Oh, randomness. Now, I guess you don't have to, we're not going to spend time doing this right now, except I will jump over to the Canvas page to show you guys up at the top. I didn't point this out yesterday, but there's this AP statistics formula sheet, especially when we get, I don't know, halfway through the class. Starting then, we are going to be referring to this formula sheet every single day. For a while, it won't really matter if you have it, but when I start referring to it, if you don't have it available, you're going to be kind of scrambling to figure out what I'm talking about. So if you have that downloaded or just easily accessible somewhere, that will be incredibly important. And this is the actual formula sheet you will use on the test, unless they change it, but it's highly unlikely it will change. Anyways, so the more comfortable you get with this sooner, the better. And if you look at it now, it might freak you out a bit. We won't worry about it. But every one of those formulas we will go through. It will all be good. Chapter 2, vocabulary. If you read, you already saw this stuff. These are just kind of generic terms that it's easy to mix them up. Most of the time, you're not going to be quizzed on like, what does case mean? What is context? You know, and even if you did, even if you were, you could probably figure it out. But there are some special terms and things that I'll say a lot, that you'll read a lot, and it's just important to understand what they're talking about. Okay, so context, what the data is about. In the textbook, they talk about all the who's, the what's, the when, the where. I don't dwell on that. So if that was confusing for you, it's not something I want you to get stressed about. Though it is important to understand the context. Where did the data come from? What is the data about? What population does this data represent? So anyways, when we talk about populations, this is all the possible cases of a particular population. This doesn't mean the entire world, but we could be interested in the population of Flagstaff. And we might take a sample from within Flagstaff. So the population would be Flagstaff. The sample would be maybe 100 people. These will be more important later, but it's worth mentioning it at the beginning. The population is not always obvious. So that will be something we come back to also. The variable. This is any characteristic or trait that can vary from case to case. That's kind of generic math stuff, but it takes on a special difference here in statistics, just in the sense that we're dealing with real data and we're not dealing with like X's and Y's, not in that mathematical sense. Cases are not variables. This is important. So when you have a data table, and we're going to see some, but when you have a data table and you have all these, I'm not writing yet, like here's all your categories up at the top. And you have all these cases, like this is person A, this is person B, this is person C, and so on. These are not variables. These are your cases. But the things about them, so if you're measuring their age, their height, their weight, whatever it is that you're measuring about these people, these would be your variables right here, but not the actual cases. Again, it's highly unlikely that's going to be a point of distinction that's going to matter, but it could be. The units, this is obvious enough, but you need to make sure you include it when you're talking about quantitative data. So of course, chapter 2 is all about identifying the difference between quantitative and categorical data. And here's just a few things we can talk about with this. Categorical data is what we use when we're referring to counts. So we're going to have categories, that's a given. And the only thing you can do with those categories is you can count within, like how many people have chocolate ice cream as their favorite, how many people have basketball as their favorite sport, how many people, and so that's, if you have categorical data, all you can do is count the number within the categories. And that's what you're limited to. The categorical data can be numerical. So you learned about this if you're talking about our zip codes. So I happen to live in the zip code 86005. A lot of you probably live in 86001, and some of you might live in 86004, and who knows, there's others out there. So, you know, if we count it up, there would be, you know, one here. Let's say 4 of us live in 86001, and 4 of us live in 86004, and let's say 6 of us live in 86005, right? All we can do is count. it's numerical, but it's still categorical data, because it doesn't make any sense when we get to quantitative. It doesn't make any sense to average this data together. What's our average zip code? That makes no sense in any context. So some data that appears quantitative can be categorical depending on how it's used. So another thing to think about is if we talked about, let's see, employees at a business, and we could just say, let's say there's all these employees. So here's 5 people, and this person has worked 10 years there. This one's been there for 3 years. This one's a new hire. This one's like been there for forever. And then this guy's been there for 6 years. Obviously, we could average and say, what's the average length someone's been at this company? But on the flip side, we could turn it categorical. We could say, we're going to have 2 categories, long-time employees and newer employees. And maybe new is less than 10 years and long is 10 years or greater. So we would have 2 long-time employees and 3 relatively new ones. So we just turned a quantitative variable into a categorical one. So I'm throwing all this stuff out at the beginning, but in the specific context we get to later, you're gonna have to figure out, is it categorical or quantitative? And that will determine what kind of tests are appropriate and things like that. Quantitative data is all about averages. If it makes sense to average the data that you have, then you're looking at quantitative. It must be numerical, and it must include. Yes.
Can I ask you a quick question?
Yes.
So could you put so like when you have the number of years and someone works 10 years, 3 years, 4 years, could you put it in a category of like, this person works 10 years, this person works 4 years, this person works that years, or can you only do it upon this person worked less than 10 years, this person worked more than 10 years?
Oh, well, you could have a category for each number of years.
Okay.
If you wanted to. Yeah. And there are, especially, we're going to talk about in the next chapter, histograms, which is really a quantitative data display, but you get to pick what your interval is. And you might already be familiar with histograms. So you're taking quantitative data and you're saying, if you're between 0 and 1 year, at least 0, but up to, but less than 1, then you're going to fall into this area right here. From 1 to less than 2, yeah. So there will be things like that. And in a sense, that's kind of turning it categorical, but that's where it's.
Gotcha.
At that point, we really call it quantitative data display.
Gotcha. Thanks for today.
Yeah. Oh no. Okay, here's what's going to have to happen. I'm going to pause this real quick. Okay, so frequency tables. I'll just bring one up. It's hard to see relative differences, but easy to find the numerical data. And what I'm saying is, when you're talking about relative differences, like they give us this tally column, so that makes it a little better. But if you're talking about how many more are in this category versus this one, if you're talking about hundreds of data points and they just give you numbers, it's kind of hard to quickly come up with like, oh, this is about 1/6. This is about 1/4. This is pretty easy because it's only 31. So my point is, if you had hundreds of data points and just a frequency table, and they only gave you this right here, a second, then it's going to be hard to see the relative differences between those. And like, how much bigger is this one than that one? Okay, but relative frequency tables, they're good for they're good for proportions, like knowing the overall breakdown and the distributions of how many are in each category. So here we have all these categories, 50, and I'm assuming, I don't know what the context is here. Maybe that's has something to do with how much people weigh. But we've got all these frequencies, and this got turned into a relative frequency in this column right here, because there were 50 people total, so 10 out of 50 makes it 20%, 12 out of 50 made it 24%, and so on. So we can see the relative differences between them a little easier. And so now it's really easy to look and say, oh, well, this one's obviously represented by the most. Again, you could look at the numbers and just see what number is the biggest. But relative frequency is a nice way of doing comparisons. And we know how much bigger this category is to this one right here, the one below it. So when it says the relative frequencies must add to 1, when I sum up this column right here, this must be 1.0. Okay. Not much more to say on that one. Bar charts. Okay. Here we go. So there are a few things about bar charts that are important to understand. Really quick visual comparison. These are very common data displays. If you want to get like the specific numbers, it can be a little hard to do that because, what is this one exactly? That's about 12% probably. But if it's a decimal, we can't really know for sure. We just get approximately what the numbers are. These categories do not have to be mutually exclusive. And what I mean by that is that, well, this one appears to be mutually exclusive. But let's say the categories were all, this is just a good one to come back to, all the ice creams that you like. I love vanilla, I love chocolate. I do not like strawberry ice cream. So I would be included in the vanilla and the chocolate column, but I would not be represented in the strawberry column. Now, truthfully, I like strawberry ice cream too. So I just lied to you. I apologize. All right, but notice these are mutually exclusive, at least the way it's set up. I think it's safe to say you wouldn't be part of multiple. Though again, race is kind of a tricky one. You can't, you know what I'm saying. Generally, you're just gonna have one race to pick from. So we could consider these mutually exclusive. If someone is in the Hispanic column, they're not simultaneously gonna be in the Black column. And if they consider themselves both, they might put themselves in the multiracial column. Okay. So again, no context here, but we can see that these bar charts can have a lot of different data that's simultaneously presented, but it's really good as a quick visual comparison. Okay, I don't know what more to say about this. But if there is anything that you wanted to come back to get clarifications on, we can do that. Pie charts. Pie charts suck. Okay. They do give a quick visual difference of relative proportions. The data here must be mutually exclusive. Okay, because the pie represents 100% of the population. So you can't have people fall into two categories, because if 75% of people like the Arizona Cardinals and 75% of people like the Arizona Diamondbacks, and you're trying to put that into a pie chart, you're going to have over 100% added up. So you have to be mutually exclusive. Maybe what's your favorite team? And maybe it could be split 50-50 at that point. Okay, so hopefully that made sense how to explain that. It can be hard to read, especially if there are two slices or if the percentages are really close. And pie charts really are, you're never going to have to create one. So just be prepared to read one. And you can see this is presumably favorite browser or just whatever the most common browsers are. And you can see, you know what pie charts are. They're just not very great. For some reason, people love them. These pie charts are pretty good though. There you go. I got a few of them you can look at. There you go. And it doesn't end there. If you enjoy pie chart humor, you can look that up. It's a thing. All right, let's move ahead. The area principle. So in bar charts, it's really important. The idea is that the area of the, for a particular category is proportional to its area compared to the population. So if you have a bar chart with different widths, and you have this one looks like this, and this one that looks like this, then you're violating the area principle, or maybe you're not, and it's kind of hard to tell. So that's one idea. And in pie charts, you want to only show a two-dimensional view of the pie, never 3D, because I think I have an example. Also, don't use pie charts, yeah. But look at this, and it's not a very obvious thing, but this area right here, because it's shown at kind of an isometric view at an angle, then this wedge of the pie actually seems to have less area than maybe it should appear to us. And maybe this one is overemphasized. You know, the areas can be thrown off a little bit by looking at it from a different view. So it can be harder to read it this way. And this is a great example of having different widths, because it makes the people from Latvia look like they're giants, and the people from India look like they're Oompa Loompas. And there's only a 5-inch difference in heights between them. So you will hopefully become very good at recognizing bad charts. Those are bad. For all graphical displays of data, make sure the labels and the scales are not deceptive. So here, let's look at this. What is the story of this chart?
Lots of ups and downs.
Lots of ups and downs. What's the overall trend of temperature from 1951 to 1980?
It's staying the same, or
Yeah,
returns.
it goes up. Perfect, perfect. It goes up, it goes down, but it stays about the same. This is misleading because here I'm going to show you the same data in a much longer time scale. So when you can arbitrarily pick your peak and your beginning and end years, you can make the data say whatever you want. So, I mean, obviously there's a trend right here, but if we had set our dates at, that's about 1943 up to about 1985, 42 years, it looks like not much is going on. It hasn't really risen. But anyways, you get the idea. Okay, so those are all kind of the simple concepts. Contingency tables, this is going to come up repeatedly throughout the semester. So if you focus on one thing in this chapter, this is going to be it. And it's going to be important when we get to probability. It's going to be important at the end of the year. So they just keep popping up. Okay, so these are data displays for bivariate data. Everything before this, a pie chart, is going to be one variable, like what's your favorite type of car? And you might have in the pie chart, oh, trucks, SUVs. Well, SUVs would be this one right here. So SUVs, trucks, sports cars, whatever. That's one variable. You can have lots of different answers, but it's one variable. So if you have two variables, like did you go to college and do you earn more than $100,000 per year? I can firmly answer yes to one of those and no to one of those. But anyways, if you had two variables that you're asking and you fit into a category, you need a contingency table to show that data. So, oh, we have a Desmos activity for this. How fun. So what you will need to do is you're going to need to navigate over to desmos.com. I don't think you need me to copy the link, but I can. And your class code when you get there, let me get out of this and go to the chat. I'll go ahead and copy this just, yeah. So you can just click on it, it should take you. But before you go, you will have a place on the very front screen, first screen when you get there, to put in a class code and put that code in. And I will meet you over there. Okay, so what we're looking at with this slide right here is, there we go, I think I can make that bigger, is we are looking at marginal distributions. And so it's not completely spelled out in this, but we're going to talk about it more anyway. So marginal distributions are going to be when you look at these column totals right here, or the row totals, and you want to figure out what proportion we're looking at for either one of those. And so in this case, we're talking about the row totals at the end. And so we're looking at no force use. What proportion? So we had 2,484 out of, this is your table total in the bottom right corner. So I just do 2,484 out of 3,164, and that's going to be the 0.785. And we can get our other numbers as well. So anyways, I didn't have my calculator set up right. So I know you guys already have these numbers, so I'll just do it very quickly, or most of you do. So this is 0.152. And remember, these totals have to add up to 1. So when I do this one, it better be something that adds up to 1. And I got 0.063. I could add those up and double check it, but I'm going to assume that's right. You guys can tell me if that all looks good. Okay, so 78.5% of, and it is good that they ask this question. A lot of statistics is putting things back into context. So much of your statistics answers when you get to your FRQs are going to be not just what is the answer, but kind of explaining, running through all the processes to get that right, and to be able to put that into context and put it into writing. So 78.5% of encounters with the police had no force used, something to that effect. All right, I'll just jump ahead from this one. They're asking us to do the same thing for this slide, except now they want us to look at the column totals right here and find those proportions. This is something like, I already did these calculations. I know you guys did too, but we have a little bit shorter time in class, so I'm going to run through this somewhat quickly. So all I did was 1,743 divided by 3,169. So these are the marginal totals and the marginal distribution. So it's going to be important, and we're going to keep coming back to this idea like I keep saying. But if you understand that much for right now, and the reason we do call it marginal, that's what this last one is saying. And I know it's not very clear, but they gave you an option to draw right here. And actually I can draw using my stylus. So it's marginal, and that's easy to remember because this is on the margins of the contingency table or the two-way table or the bivariate table. Lots of different names for this. So anyways, on the margins, you get your marginal distribution. So hopefully you can remember that. In the middle is where you get your conditional distributions. So it's a probability distribution for a subgroup. So anyways, we can just jump into this. So we're going to find the conditional distribution for each race. So we're only looking at black and white, so we're not worried about this column for this particular calculation. So here's the way that we say this. On the condition that we're looking at a black suspect, black suspect, what is the distribution of force level? So we would be doing 1,371 out of 1,743. You guys can do that check at home. And this is going to be 0.787. On the condition that the suspect is black, what is the proportion of hands used? So that's going to be 263 out of 1,743. So you can see it's on the condition. And so when we say it's on the condition, I am limiting my view of this table to that column only. So if that helps you think about it, when I do that, I get 0.151. And then the last one, 109 out of 1,743 would be higher force level, and that's going to be about 6%. Okay, now if we do the same thing on the condition of being white, now I'm restricting myself to this column only. So 260 out of 308. 260 divided by 308 gives me 0.844. And then 30 out of 308 is 0.097. And then finally 18 out of 308 is 0.058. So I hope you guys are kind of plugging those numbers in and double checking me. So of course you can see that when you do the relative distribution, especially these the conditional distributions here, you can actually start drawing some statistical conclusions from the data. And you'll have a chance to kind of comment on this in a minute, but I mean, honestly, you could do it now. So if you're kind of thinking through what the data is showing us now compared to what it showed us before, we can see what relative frequency gives us. And what do you guys notice?
That among black suspects, there's a high level of force use compared to white. There's like a higher level in
More force use, period.
There's more force use is what I'm trying to say.
Very good. Yeah. Yeah, very good. So that's kind of one takeaway you can have. I think there's a slide that asks you to kind of comment on it. So, I mean, in context, now this is a good thing. I'm going to get rid of this, but they're asking about this 84%, right? So I'm going to go to the next slide and notice that this is the proportion of white suspects who had no force used. And so that's kind of what they're asking here. 84.4% of white suspects had no force used against them. Now it's important that we put that entire context because it's conditional. And I'm not actually going to write it out, but you can see that. Okay, so here's one possible way of reading the data that says police had no force interactions with only 260 white suspects. Meanwhile, a much higher number of black suspects, 1,371, didn't experience force. Clearly, black people experience force-free interactions with police more frequently than white people. Now, you could kind of answer two different questions. Is that accurate, and is it a good analysis? So is that an accurate observation?
No.
Well, what do you guys think? Anyone else?
It's an accurate representation of it. Like it's an accurate representation of the data, but it's not a good analysis because only a fewer amount of white suspects were actually checked. Where it was only 308 white, and then it was 174. So there's a higher percentage who are black, which kind of skews the data.
There you go. So it is accurate in the sense that there is no lie right there. More black people did experience force-free interactions, but that's because more black people had interactions with the cops in the first place. So it's leaving out context. So I think we'd all agree it's an incomplete analysis of the data. I hope we'd all agree. Okay, so they already give us this stuff right here. And the other thing that you can do with bivariate data, there's another display that we can do, which you can have bar charts to show this. And I think in a minute, we're gonna look at segmented bar charts. That'll be in a little bit. So if you already read the chapter, you already know about segmented bar charts, and we'll look at that. But you can see now a quick visual comparison that shows the difference. Honestly, there's not a great deal of difference between these two, but when you compare it to white, we can see there is an obvious jump up and then drop down for those two. This actually doesn't look much different, but certainly that one does. So good visual display here. And notice that your axes on the left in the y-axis, they're labeled with percents because we're looking at relative frequencies. So a good label for your table is going to be super important. Okay, so they do want us to make a segmented bar graph right here. And if we have these numbers, 78.7, I'm just going to create this one with you guys to see. So we've got these numbers. I'm going to try and remember it. 78, I'm just going to say 79%, 15, and 6, 84, 10, and 6. 79, 15, 6, 84, 10, and 6. So, and this is only for black and white. So I'm not going to be able to shade in the Hispanic. But black was at 84. So I could put something right there. So no force. I'll just do kind of these dash lines like this. And for white, I think it was 79, something in that range. No. I'm getting my numbers backwards, aren't I? Yeah, black had 79, white had 84. See, there I go. What am I going to learn? Okay. So white should be at about 84. This is 79. Okay, and so now we can see where the no force is. What's great about these segmented bar graphs is that we're looking at a 100% total right here at the top. And so we can kind of get a really quick comparison between them. It's about 15%, put me to about right here. So I'll do this one as a hash thing going on. So I'm going to have go in both directions. 10% for white puts it about right here. And then, of course, the leftover, I'll just make solid color. All right, so now we can do this kind of side-by-side comparison between the two, and we can see kind of how that breaks down a little better. So rather than having 3 different bars for the different levels of force, we're going to combine them all into one. Okay, I don't want to say too much more about this. In fact, we're going to stop it there. I'm going to go back to the presentation now so that we can talk about some other concepts. Okay, so thank you guys for patiently following along. I told you you're going to get to hear me talk a lot. All right, so this is maybe one of the more confusing concepts that show up in this chapter. And hopefully when we talk about it, it's not that bad, but it can be a little bit mind-bending trying to wrap your head around this at first. So variables are independent when their conditional distribution is the same for another variable's conditional distribution. Okay, and that's not, I don't even think that's very good wording for this. I think it's better just to look at it in context. So if we look at these two tables, and I'm going to come to the one on the left. Actually, let me start with the one on the right. So we're looking at presumably some class and a certain number of males passed and failed, and same for females. So the question I might ask is, knowing that the student is a female, does that have an effect on her ability to pass the class? Or vice versa, knowing that a person passed the class, does that affect the likelihood that it's male or female, that person is male or female? So if I ask that question, I'm really asking a question about independence. And that still might not make sense, but let's see what we're going to do. I'm going to decide to do a conditional distribution based on race, or not on race, on gender, I'm sorry. And I'm going to figure out the conditional distribution for males passing and failing the class. So 66 out of 110 is, how about that, 0.6. So I'll just put this over here. That's 0.6, which means this is going to be 0.4. For females, it's 54 out of 90, which is 0.6 and 0.4. So my takeaway from this is that since males and females passed the class at the same rate, in the same distribution, then it seems like there's no association between being male and or being female and being able to pass the class. This does not have an effect. So and this is where it's a little bit strange, but if these, at this point, I would say these two variables are independent. So grade and class, grade and gender, are independent. And further, I could say there's no association between them. And just to reiterate it, when I say there's no association, that means if I gave you a heads up that you're looking at a student who happened to fail the class, that's not going to give you a hint. You're not going to be able to have any idea, okay, great, they failed the class. That still doesn't help me determine if it's male or female, because there's no association between gender and passing or failing the class. Now let's compare that to the other table. So in this one, we can see, just looking at it, there's an obvious difference between these. And I'm assuming this, well, yes, this is definitely made up data. There's no way there's this big of a difference. But if I look at, we'll look at gender again, we'll do a conditional distribution. Now I guess we're looking at favorite animal. So 42 out of 52, if I'm doing the conditional distribution, this is 0.81, which means this one better be 0.19. Oh yeah. So if I do the same for the conditional distribution of females in favorite animal, 9 out of 48 is 0.19, which means this is going to be 0.81. So we can see that if I, at this point, if I told you, oh, this person has a favorite animal as a cat, then according to this data, you would probably be thinking, oh, their favorite animal is a cat. It's probably a female. It's most likely a female. And according to this, that, because these are not independent. So what we could say here is that gender and favorite animal are not independent. And this is the way that we say it. We say that they're not independent. We don't say that they're dependent. We say that they're not independent. And that means that there is an association. Okay. So is that making sense for right now?
Yeah.
Okay, good. Now, one kind of thing to keep in mind, at the end of the semester, one of the last things that we learn, we're going to figure out how we can mathematically determine if there's independence or not. But for right now, your basic strategy can be if they're within about 3%. So let's say I gave you a different conditional contingency table, and I'm just going to make up some numbers right here. So if this was at 0.64 and 0.36, and this is 0.67 and 0.33, that's close enough that you could say they're probably independent. If it's close enough, they are independent. And I can't really determine favorite animal from gender. Okay. Actually, I'll leave that up. I don't know if anyone was trying to write anything, but that's the basic idea of independence. In the last little bit of class, we need to talk about a couple more things. I'll try and do it as fast as possible. Is everyone good? Okay, let's move ahead. We already talked about segmented bar charts, so luckily I don't need to go into that any further, but you'll notice this one's a relative frequency segmented bar chart. So they're all going to have the same height. They're all at 100%. This is a frequency segmented bar chart. So this can be helpful in its own way, but obviously they're going to have different heights, but we still get the breakdown. So this is about 50-50 split. That looks like about a 2/3 to 1/3 split, and another 50-50 and so on. But, you can kind of read that. This is the fun one, Mosaic Plots. And part of your homework tonight is to read more about Mosaic Plots. I will tell you, I will not ever make you create one, but it's actually a more useful segmented bar chart. And okay, here we go. Well, let's look at it all before we kind of try and work through it. So the entire area here, well, this is a big square, right? And this represents 100% of the population. And this happens to be Titanic, people who survived and people who didn't survive. Okay, so 100% of the people on the Titanic, we're going to break it down according to, first of all, and this is what we do. We start at the bottom and we work our way around clockwise. So I'm going to start with sex. So I've got female and male. I'm going to get rid of everything so we can read this. So females and males. And notice that these are just two bars that have been created. So to the left of that line represents the proportion of females on the Titanic. To the right of it represents the proportion of males. So just right now, I would guess this is about a, I don't know, 0.65 proportion of males and then a 0.35 proportion of females. All right, so that's good. Now, as we move around to passenger class, I've got first, second, and third. All right, and actually one thing they're not showing us is the crew. So this is not the entire population of Titanic, but you get the idea. So for each bar, for the females, this is broken down. It looks like there's quite a few who were in first class compared to men. So proportion-wise. And then there's probably a pretty even proportion breakdown between men and women in second class. And then there are obviously higher proportion of males in third class than there were females. But now we go all the way up to the top, and this 0 and 1 represents survival and dying. So 0 is dead. I guess they're all dead now. 1 means they survived. Okay. So now we can see within these boxes, let me actually clear all this again. So within this box, we can see a pretty high proportion survived. If you're a female first class, you know, must have been pretty nice for you. You know, if your ship is going to go down in the middle of the North Atlantic, you know, it helps to be first class female. All right, if you were a third class male, your odds were not so high. Okay, so here's the great thing about the end of this. So if you were asked to interpret part of this, the area, this box right here, this represents the total area out of the full population. So this proportion in area is going to be the same as the proportion in numbers. So I would just guess this is about 1/16 of the total area. It's just a, you know, an estimation. So this would be about 6%. 6% of the people on board were males who were first class and survived. All right, so is the Mosaic plot making sense? Okay. Again, if you have questions on this and you want to look through it more, we can stay out after class and do that. So you will not have to ever create one of these, but there is a document that I want you to look through that does show you how you would create this. Okay, and notice this is actually 3 variables, gender, class, and survival. So that's what another thing Mosaic plots can be used for. You could even split this further if you wanted to add one more variable right here, like, I don't know, whatever a 4th variable could be, you could split this one more time this way. How fun would that be to try and read? Okay. Simpson's paradox, this is the last thing. Here it is. Okay. Let's look at Simpson's paradox. Sometimes, and there's a really good example in your textbook, if I recall correctly. So the idea behind Simpson's paradox is that the overall distribution with many categories combined can paint a different picture from what happens if you look within each category. So the marginal distributions can paint a different picture than the conditional distributions do. And this is a classic example. So if I only give you this data right here, it says that this was, I think it was Stanford, or no, it was California, Berkeley. It was a college. That if you look at the percent that they admitted, 8,442 men applied and 44% were admitted. 4,321 women applied, 35% were admitted. And with this alone, it sure looks like there's some kind of gender discrimination going on. But this is, again, a great example of Simpson's paradox, because let's break this down a little further. And now, I will say the numbers don't quite match up here, but the idea is correct. So this might not be correct, or some of these numbers might be incorrect. But whatever the case, the idea is correct. And this is based on a true thing, a true actual court case. And this evidence came out during the court, the trial itself. So let's kind of see what happens. Within College A, I don't know what these colleges represent, but within College A, 62% of men were admitted, but 82% of women were. Okay, so here, women were admitted higher. In College B, 63% of men versus 68% of women. All right, we can see they bold the ones that come out ahead. So I'll just run down really quickly. So this is not showing any evidence of discrimination. Or, I mean, theoretically, you could say there's discrimination against men, but there's only this one that's wildly different. And so it looks like it's a pretty fair selection process that they went through. So why does the overall story paint a different picture? What do you guys think?
There's just a lot more men than women.
Well, there's a lot more men than women. That alone wouldn't explain the difference. So look at the conditional distribution of where the men and women applied. Where did most women apply to?
C.
C. So most women applied to College C, and most men applied to
A.
A. Now, if we compare those two departments, A accepts way more people across the board than C does. So a higher relative proportion of women applied to a more selective college. And if you look at these four down here are the four that women applied to the most, C, D, E, and F, and all of them have more selective criteria. But men preferred these two colleges primarily, and they admitted way more people. So within individual colleges, there's no discrimination. It's just where men and women chose to apply that created this overall discrepancy. So that's the idea of Simpson's paradox, and we're going to see it in different contexts as well. So there we go. That's kind of the idea. And as far as what kind of questions you might have related to Simpson's paradox, you can, it will come up again. So it's kind of hard to talk about it now, but you can notice these trends in different ways, like in scatter plots when we get to those later. So you might have questions where it shows an overall trend and then a trend broken down by category, and you can kind of notice Simpson's paradox at play. Okay. So it's just important to understand the concept behind this. And that's about it for today. We finished with 5 minutes. Again, we got all the way through chapter 3, so that's pretty good. And your homework, oh, I need to change this. These are dates from last semester. But you need to read chapter 4. We're going to look through that one tomorrow. There's a document about the Mosaic plots, and then there are some problems posted. Just a reminder, if you look through the problems and you know how to do it, skip it. If you don't know how to do it, try and do it. If you have any questions, you can stick around. But besides that, you can have a wonderful day, and I'll see you tomorrow.